Now, I have to attend a meeting after our class, so I might have to end early today. All right, so don't be disappointed if I stop class early, which I don't think anybody is. How early is early? I don't know, maybe 10 to, 5 to, something like that. We'll see how it goes. Okay, so we're over here. I'm aiming for finishing 3-2, maybe just sneak in a little bit of 3-3, and that's about it. Okay, we'll have a quiz on Friday as usual. I'll tell you more about it perhaps tomorrow. And for our quizzes, you don't really have to study because you get to help each other out and you have the whole weekend to work on it. Okay. All right, so I'll try to finish up 3.2. I was going to go back and do some problems from 3.1 also, if I have time, and then maybe introduce 3.3, and maybe that's all the time we got. All right. Okay, now on page 187, 3.2, there's a nice little table at the bottom here. You can put all of them on your cheat sheet if you want. I don't think you need to. Again, if we were meeting face-to-face, I'd make you guys memorize these all, but since we're not, you can't. And by the way, maybe next semester when you take Calc 2, your Calc 2 teacher might insist that you have all of these memorized. So just warning you of that possibility. And that might be true whether or not we're still under quarantine or we can, meet face-to-face. Your next teacher might insist that you know these. So anyway. All right, so in the bottom of 187, the derivative of a constant function is 0. Please notice a different notation. D dx means derivative, but also you can just put the prime, which I like better. I mean, it's a lot shorter to just put prime, the apostrophe, than it is to keep writing d dx. But anyway, the power root, the derivative of x to the n x to the n minus 1, where n is any real number. So it can be positive, negative, fractions, decimals, whatever. The derivative of e to the x is itself, e to the x. Later we'll learn how to differentiate 2 to the x, 3 to the x, 10 to the x, and so on. They're not as easy. So the nicest exponential function to differentiate is e to the x. Okay, the constant multiplier rule. CF prime, if you have a constant times a function, the derivative is a constant times the root of the function. Okay, sum and difference rules are intuitive. F plus g prime, f prime plus g prime, f minus g prime, f prime minus g prime. Okay. Unfortunately, the product and quotient rules are not as nice. Okay. They're provable. I just kind of flashed the proof on you real quickly. You can look at it or not. But here we go. Fg prime is fg prime plus gf prime. In words, first times the derivative of the second plus the other way around, second times the derivative of the first. And in the quotient root, f over g prime, okay, it's the most complicated of all, gf prime minus fg prime all over g squared. Okay, in words, I said the denominator times the derivative of the numerator minus the other way around. Notice for the product root, it's a plus. For the quotient root, it turns out to be a minus. Minus the numerator times the derivative of the denominator, all divided by the square of the denominator. Okay. All right, so I'll do a bunch more of these problems from section 3.2. And here we go. Okay, so 3.2, how about 17? It goes y equals e to the p times p plus p radical p. So the variable here is p. So if you were to use the d notation, the Leibniz notation, you would write dy dp. It clearly tells you the variables are y and p. Okay, so I'm going to first write that as p to the 3/2 power, e to the p times p plus, this is p to the 1, this is p to the half. So when you add them together, you have 3/2. All right, then I will do the product root because it's something times something. Now you might say, can I distribute? Yes, you're allowed to distribute, but in that case, you'd have to do the product root twice. So yes, you could go p e to the p plus p to the 3/2 e to the p. And when you stop and think about it, you have to do the product root twice. If you just leave it as is, you only have to do the product root once. So there we go. All right, so this is the first function. This is the second. So first function, e to the p, times the derivative of the second. The derivative of p is 1. Derivative of p to the 3/2 is 3/2 p to the 1/2. Plus second function, p plus p to the 3/2, times the derivative first, the derivative of e to the p is itself, so e to the p. Okay, I'm going to stop there. I mean, you could clean up the algebra. It's very messy. We're focusing on the calculus now, not on the algebra. Okay. Now, if you're not sure on a quiz or test, should I go farther or not, you can always ask me. But our focus is on the calculus. Okay. We could multiply all that out, but we don't really feel like it. So that's it. Okay. So I'm focusing now on the calculus. Okay. Here's 21. F of t equals cube root of t over t minus 3. Right. Now, cube root of t, think of it as t to the 1/3 power. All right. Now I do the quotient root, which I put down here from yesterday. Okay, so you start off with the denominator, t minus 3, times the derivative of the numerator, okay, f prime. So what's the derivative of t to the 1/3? 1/3 t to the negative 2/3. Right, 1/3 minus 1, negative 2/3. Okay, then minus f top cube root of t times the derivative of the denominator. What's the derivative of t minus 3? 1. So if it's times 1, you don't really have to write it. All over the denominator squared, so t minus 3 squared. And again, for now, I'll just stop. Yes, if you felt like it, you could try to clean it up. I don't think it's worth it. We'll just stop right there. Yeah, there's a negative exponent, but it's even clumsy to do that. Yes, there's a 3 there. It looks messy. So if our object is to clean up the algebra, we would do so, but we're focusing on the calculus right now. So I'm going to stop right there. Okay? In case you're wondering, no, you're not allowed to cancel this out. Right? Mentioned that yesterday. That g and that g squared is always going to be there, but you cannot cancel once you subtract something. Okay? You can cancel if by chance this thing came out to be a 0, right? If that's 0, then you're allowed to cancel. Okay? So again, because of that minus sign, do not cancel t minus 3s. Okay, so I'm just going to stop there. And then 23 is also quite messy. F of x is x squared e to the x over x squared plus e to the x. So again, that looks like a quotient. So do the quotient root. Right, so bottom, x squared plus e to the x, copy it, times the derivative of the top. So if I differentiate the top, it's a product root. So here's a case of a product root inside a quotient root. Right? It's a quotient, something divided by something. And then I have to differentiate the numerator, but that's a product in itself. Okay, so in the process of taking the derivative of the numerator, I have to do the product root, which is first function, x squared, times the derivative of the second, derivative of e to the x is e to the x, plus second function, e to the x, times the derivative of the first. So what's the derivative of x squared? 2x. So I've done gf prime minus fg prime. So it's the numerator, copy the numerator, x squared e to the x, and then times the derivative of the denominator. So what's the derivative of x squared plus e to the x? 2x plus e to the x. All over the square of the denominator. So I'm just going to write it as x squared plus e to the x squared. And again, for right now, I'm just going to stop. It's a lot of very messy algebra. You could clean it up if you want to. I don't really want to. You probably don't want to either. Okay, okay, so we're just going to stop right there for now. All right, then I was going to show you 27. Okay, f of x equals x cubed plus 1 e to the x. Okay, this one I'm actually going to clean up because it's not that bad. All right, so first function, second function, product root. So product root, f prime of x, first function times the derivative of the second. So what's the derivative of e to the x? E to the x. Plus second function, e to the x, times the derivative of the first. So what's the derivative of x cubed plus 1? 3x squared. All right, now this one you want to clean up, and besides, we have to find the second derivative, f double prime, so it's better to clean it up. I will factor out the e to the x, and then I notice I have x cubed plus 3x squared plus 1. So I'm going to write it as x cubed plus 3x squared plus 1 e to the x. And now that's easy to take the second derivative. Okay, so this is the first derivative. We're asked to find f double prime now in this problem. Okay. Oops, right here. Find f double prime of the given function. All right, so now for the second derivative, what is the second derivative? It's the derivative of the derivative. So I take the derivative of this. First function, second function. So copy the first times the derivative of the second. Derivative of the second is e to the x. Plus second function, e to the x, times the derivative of the first. So what's the derivative of all this? Derivative of x cubed is 3x squared. Plus the derivative of 3x squared is 6x. Plus the derivative of 1 is 0, so you don't have to write it. And once again, I'll just combine like terms, factor out the e to the x. So I have x cubed, I have 3x squared and another 3x squared, so that's 6x squared. And then if I take a look, I still just have a 6x and a 1. So final answer is parentheses x cubed plus 6x squared plus 6x plus 1 times e to the x. Okay. So that's it for that one. Okay, and then 35. Again, skip anything that says a graphing calculator icon. So even if I don't say so, once you see this thing, right, then ignore it. Okay, the curve y equals 1 over 1 plus x squared is called a which of Maria Agnesi? And don't worry about the name. Okay. Find the equation of the tangent line to the curve at the point -1, 1/2. Aha. So you'll see that theme over and over and over again. So whatever this thing looks like, you take the derivative, plug in -1, and then do your y minus y1 equals m times x minus x1. Okay. So y equals 1 over 1 plus x squared at the given point. So this thing has some shape. Here's a given point. Find the equation of the tangent line. Okay, so whatever this looks like, there's a tangent line somewhere. We're finding the equation of the tangent line. All right, so quotient root. Denominator, 1 plus x squared, times the derivative of the numerator. What's the derivative of 1? 0. I like that. So 0 times all that is 0, so forget about it. Minus the numerator, so minus 1, times the derivative of the denominator. Derivative of all this is 2x. All over 1 plus x squared squared. Okay? And then just rewriting this as negative 2x over 1 plus x squared squared. Okay, so that's my dy dx. What's dy dx? Derivative, same as y prime, same as f prime of x. Okay? The nice thing about the derivative, this gives me the slope anywhere on the curve. Anywhere on the curve, if I want the slope, I plug in here. Like if I say, what's the slope at x equals 0? Plug in 0, you get 0. So that means at the origin, the slope is 0. We would have a horizontal tangent. Now, where do we want the slope? At -1, 1/2, I plug in x equals -1. So what about the half? That would be for y. My expression doesn't have any y, so don't worry about it. And later on, we will have our derivatives that have x and y, in which case we plug in both of them. Okay. Or another way of saying it, even now, is to say, okay, for your derivative expression, everywhere you see x, plug in -1. Everywhere you see y, right, plug in a half. Well, I have plugged in 1/2 everywhere I see y because I don't see any y's, right? So technically, I guess you could say that. Okay, so plug in -1 here and here. So I have -2 times -1. Okay, you've got to be careful with this. This is not 0. -1 squared is 1. 1 plus 1 is 2. So I have +2 over 2 squared, 2 over 4, which is 1/2. Okay, so slope is 1/2. The point is -1/2. And there we go. Y minus y1 equals m times x minus x1. Y minus 1/2 equals 1/2 x plus 1. Stop. You do not have to go any farther with that. As we said, we know we could put that as y equals mx plus b. That's for Algebra 1 students. You're all very good in Algebra 1 because you're taking calculus, so we're not going to fool with it. We'll just stop right there, and that's good enough for me. Okay. All right, so that's it for that one. Okay, and I actually wanted to go back and do some problems from section 1 because some of you had questions about that. So 3.1, number 53. Somebody asked about sort of a mini word problem. It talks about Boyle's law. So some of you may have heard of Boyle's law in chemistry or physics, but if you've never heard of it, that's okay. Boyle's law states that when a sample of gas is compressed at a constant temperature, the pressure P of the gas is inversely proportional to the volume V of the gas. Okay, so the way to set that up from algebra is P equals K over V. You might remember having that language in algebra. Okay, the pressure is inversely proportional. Inversely proportional means K over V. Okay, and a side note, if you multiply both sides by V, you have PV equals a constant, which some of you may have heard from your chemistry or physics classes. Okay, pressure times volume, PV equals a constant. So P is equal to K over V. Okay, and what's going to happen is you start plugging in stuff. You plug in the P and the T, or the V rather, to solve for K. And then once you solve for K, then you can answer any questions after that. All right. Let me show you what's happening. So P equals K over V. Okay. Then they told me to plug in 50 kilopascals and 0.106 for the volume. Volume was in cubic meters, I think. Yeah, meters cubed. All right, so I just plugged those in and multiplied these two together, and K is 5.3. In other words, 50 times 0.106. If you multiply both sides by 0.106, then K is 5.3. So P is K over V. P equals 5.3 over V, okay, which I could also write as V equals 5.3 over P. Do a little bit of algebra there. Okay, what do I want to do that for? In the problem, it asks for dV dP, okay, rate of change of volume with respect to pressure. So notice a good thing about the Leibniz notation. You know right away it's volume. How does it change as pressure changes? So I need to solve for V. Okay. I'm not sure if you've seen this shortcut before, but when you have an equation like this, you can simply just reverse them. Put the V here and the P here. Have you ever seen something like that? Okay. If you haven't, now you've learned it. Okay, so if you have something like this, P equals 5.3 over V, you're allowed to just reverse these two. Okay. The logic is if you multiply both sides by V, you have PV equals 5.3, and then just divide both sides by P. It looks like this. Okay, so in order for me to use the power rule, write this as 5.3 P to the minus 1. By the way, can I use the quotient rule here? Yes, you can use the quotient rule. Quotient rule is probably one of our least favorite because there's so much stuff. It's a lot easier to think of it as 5.3 P to the negative 1. And then I'll just use the power rule and the constant multiplier rule. Okay, so V prime, or you can say dV dP as it says in the book. Okay, so negative 1 times 5.3, negative 5.3. P to the negative 2, right? So negative 1 comes down, hits the 5.3, becomes negative. And then negative 1 minus 1 is negative 2. And then rewrite it as negative 5.3 over P squared. All right, and then they tell me to plug in 50. So calculate dV dP when P is equal to 50 kilopascals. What's a kilopascal? It's a measure of pressure. Don't worry about it too much. So I plug in 50 squared and round it up to negative 0.00212. cubic meters per kilopascal would be the units. Okay? Units of volume, cubic meters, units for pressure, kilopascal. Okay? And it's a negative, so that means if I increase the pressure by 1 kilopascal, the volume would decrease by 0.00212 cubic meters, which makes sense. Like if you're compressing a gas, if you have a gas and you're trying to compress it, okay, so you know that if you increase the pressure, the volume decreases, and here's the rate of change at this particular moment. Okay? So if I have the number of kilopascals go up by 1, the volume decreases by 0.00212 cubic meters. Okay, so that's what that means. Okay, the other one I wanted to show you from section 1, page 181, 3.1, 59. Find equations of both lines that are tangent to the curve y equals blah, 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 and are parallel to the line 3x minus y equals 15. All right, so we're saying here's a curve. We want the tangent to be parallel to this line. So parallel lines have the same slope. So first I have to find the slope of this. Okay, so here's the way you do that. All right, so here's the function, parallel. So if I draw two tight lines like that, that means parallel to 3x minus y equals 15. Okay, so to find the slope, I make it look like y equals mx plus b. I add y to both sides and I subtract 15. It'll look like this. So you can read off the slope is 3. What's the slope of the line that I want? It's also 3 because parallel lines have the same slope. Okay. Now, yesterday we had something where it was perpendicular. So I had to first find the negative reciprocal, and then I put something like m wanted, W-A-N-T-E-D. The slope that I want would be negative 1/3. In this case, I decided not to put m wanted because it's going to be the same. You want parallel lines. Parallel lines have the same slope. So the slope that I want is 3. But yesterday, when I put m and subscript it with wanted, that's because I didn't want the original one. I needed the negative reciprocal of that. So that's why I wrote m wanted was the negative reciprocal. So in this particular case, if it asks for the perpendicular, the m that I want, or I would write m wanted, would be negative 1/3, the negative reciprocal. But in this case, since I want parallel, I just keep it as 3. So I want the derivative to equal 3, i.e. slope equals 3. There's 2 such points. So I take the derivative. So that's easy for polynomial. So the derivative of x cubed, 3x squared. Derivative of negative 3x squared is negative 6x. Derivative of 3x is 3. The derivative of negative 3 is 0. Okay, and I want to set it equal to 3 this time. Where is the slope equal to 3? Where is the slope parallel to this? Right, well, this has a slope of 3. If it's going to be parallel, I need the slope also be 3. If it said perpendicular, I'd have to make it what? Negative 1/3, negative reciprocal. Okay, so I solve this. Subtract 3 on both sides. 3x squared minus 6x equals 0. Factor out to 3x. So 3x parentheses x minus 2 equals 0. So I just set each of these to 0. 3x equals 0 means x equals 0. And x minus 2 equals 0 means x is equal to 2. Okay. Now, it did say points, not just x coordinates. Find the equation of both lines that are tangent to blah, blah, and a parallel. Okay? So I'm going to et cetera this. I'll get you the points. So x equals 0, plug in 0, 0, 0, 0, negative 3. I did the easy one. So you do the 2, plug in 2, and then do the equation of the tangent to the curve. So I'm going to abandon the problem there. I'll just say et cetera. You get to do the rest. But you can do point slope. Well, you know the slope is 3. So you're going to go y minus a negative 3 equals m, 3 parentheses x minus 0. And then do the same thing for this one. Once you figure out the y coordinate, you just plug it in. All right, so those are some extra problems from 3.1. And now I'll go back to 3.2, and I'll do 30. So let me turn the book, 3.2. Okay. 31. No, 37, sorry. 37. but isn't it? I do want 31, sorry, 31. Find the equation of the tangent line to the curve at the specified point. Okay, so similar theme. Find the derivative, quotient root, plug in 1, 0. Okay. So here we are. So very recurring theme. Find the equation of the tangent line to the curve, blah, 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 at the given point. So you have a point, you need a slope. How do I find a slope? Slope means derivative. Okay, so I need to find the derivative. All right, so quotient root. Denominator, x squared plus x plus 1, times the derivative of the numerator. What's the derivative of x squared minus 1? 2x. Minus the numerator, x squared minus 1, times the derivative of the denominator. So what's the derivative of the denominator? 2x plus 1. All over the denominator squared. Okay, I could clean it up, but it's not necessary. They tell me already to plug in 1. When I plug in 1, I'm sure a lot of this will clean up automatically. Okay. So I want y prime of 1. What about the 0? Well, 0 is for y, but notice the derivative so far doesn't have any y's. Okay, so just plug in 1. So 1 plus 1 plus 1 times 2 times 1 minus, okay, look over here. If you plug in 1, this is 0, right? And 0 times that is automatically 0. So I'm subtracting 0. I like that. And then 1 plus 1 plus 1 squared. All right, so that's 3 times 2 divided by 3 squared. That's a square there. So 6 over 9, 2/3. So my slope is 2/3. Whatever this graph looks like at the point 1, 0, the slope of the tangent line, right, is going to be 2/3. All right, and then point slope form. Y minus y1 equals m 2/3 x minus x1, x minus 1. Stop. You can just forget about it after that. All right. Okay, so that's as much as I was going to do from 3.2. So as far as the schedule is concerned, we're good. So I've pretty much done 3.2. Which was on par. I'll sneak in just the beginnings of 3.3, and then I'll stop a little bit after that. I know some of you may have a chat question, so I'll check that in a moment. Okay, so 3.3, introduction, is the derivative of the trig functions. Trig function derivatives. Sine, cosine, tangent, cotangent, secant, cosecant. Okay. Again, I'll just give them to you. They're derivable. You can work them out. Okay. If we had time and we were in face-to-face, I would show you more of it. But now that we're under our shelter-in-place and so on, I'm not going to do it. Okay. There is one limit that you want to know, and we actually went over this. Okay. You might recall this looks like question number 9, I think it was, on the last test. Limit as theta approaches 0, sine theta over theta is equal to 1. Okay, you can make a table of this, okay, but this limit comes out to be 1. A very easy thing to do, which was like question 9 on the test, I think it was, is, well, if this is true, let me plug in 0.0001 or something like that. Okay, and you better be in radian mode. Okay, so I'm going to check to see if I'm in radians. Okay, so on my calculator, it does say radians here somewhere. They're radians, degrees. Okay, so how about I'll do sine of 0.001 divided by 0.001. Okay, that's a number that's close to 0. Remember we did something like this on the exam, right? 0.99999, there's a whole bunch of 0.999s. It's 1. So this limit is 1. Limit as theta approaches 0, sine theta over theta equals 1. You can memorize it. You can put it on your cheat sheet, or you can always do what I do here. Okay. Now, last time I taught this course, I made my class memorize it sort of, but I told them if you ever forget, you can easily just literally do like, okay, I forgot what it was, plug in 0.001 or negative 0.001, and you'll get 0.9999, right? So the limit turns out to be 1. All right, so here's a nice limit. There are some homework problems later that involve that limit. Okay, so we'll get to that. Okay, so the biggie for now, before I'm just about done, 3.3, page 193. Here are the 6 trig derivatives. Okay. How do you prove them? By using the limit definition. So I'll just mention, if you wanted to prove the derivative of the sine function, right, you would go limit h approaches 0, sine of x plus h minus sine of x all over h, and do a bunch of stuff. But this is what it comes out to be. Okay? And again, you can put it on your cheat sheet, although if we were meeting face-to-face, I'd make you guys memorize it. Your Calc 2 teacher might make you memorize it, but here we are. The derivative of the sine of x is the cosine of x. The derivative of the cosine of x is negative the sine of x. Okay, so derivative of sine is cosine, derivative of cosine is negative the sine of x. Okay, tangent and cotangent. Derivative of the tangent of x, this d dx means derivative, is secant squared x. Derivative of tangent x is secant squared x. Derivative of cotangent x is negative cosecant squared x. Okay, so secant squared, cosecant squared. And then last but not least, cosecant and secant. Okay, I'm going to start off with the secant. Derivative of secant x is secant x tangent x. The derivative of the cosecant x is negative cosecant x cotangent x. Okay, the way to prove this one, this one, this one, and this one is just to use the quotient rule. So you would derive the formula for the derivative of the sine and cosine, but all 4 of these are basically just quotients after that, because tangent is sine over cosine, and by that time you would already have these derivatives. Cotangent is cosine over sine. So if you were to do the quotient rule, this is what you would end up with. And cosecant is 1 over sine, so you could do the quotient rule. And secant is 1 over the cosine, so you could do the quotient rule for those, and this is what you end up with. Okay, so derivative of the sine is cosine, derivative of cosine is negative sine. Derivative of tangent is secant squared, derivative of cotangent is negative cosecant squared. Derivative of secant is secant times tangent. Derivative of cosecant is negative cosecant cotangent x. Okay, I will say this, if you had to memorize this, there's one memory trick. Say, how do I remember which ones are negative and which ones aren't? Okay, notice which ones have a minus sign. Cosine, cotangent, cosecant. Okay, so the co-functions have a negative, if you had to memorize it. So cosine, cotangent, cosecant all have a negative. So if there's no co, don't put the minus sign. Sine, tangent, secant. There's no co in front of it, right? So there's no negative in front of it. So those are the 6 trig functions. Okay, so go ahead and put these on your cheat sheet. I'm not going to make you guys memorize it, but beware, maybe your Calc 2 teacher is going to make you guys memorize it. I'm not sure. Okay. All right, so that's as much as I was going to do. Let me stop the share and check the chat. Maybe Prasanna already took care of it for me. Let's see what's in the chat. Okay, how do you know when to use d dx or dy dx? Anytime you want. So whenever you want to use, it's fine anyway. Okay, and let's see. Prasanna, you already got it. So yeah, if they give me y equals blah, 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 then you would say f prime or dy dx. That would be fine. If you want to go straight to it, you can put d parentheses, blah, 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 and that would also work. Okay, use the definition of the derivative. You really don't want to anymore, right? That takes way too long. So forget about that. Okay. All right. Let's see. Yeah, I'm okay with stopping now. So does anybody have a quick question? Otherwise, that's it for today. I got to go to a meeting. And then, so tomorrow we will start the next section. Friday I'll get a quiz. I'll announce tomorrow, what might be covered on the quiz. Okay. So anybody else? Let me check the chat. Okay, that's about it. So. Anybody? Give you a few more seconds. All right, I don't hear anything. All right, that'll do it for today, folks. So have a good afternoon, and we'll see you tomorrow. Okay, bye, everyone. Thank you.
Thank you.
Thank you.